Friends, let us continue our discussion of sorting algorithms of the previous two lectures. Well, we discussed a number of sorting algorithms, namely insertion sort, bubble sort, selection sort, etc. And as I mentioned, that none of these algorithms is better than the rest of the algorithms for all type of sequences. Therefore, all the algorithms survive. Now, what is the way of comparing algorithms for being better or worse than other algorithms? Friends, this is subject matter of analysis of algorithms. What may be the criteria for comparing algorithms? Naturally, the resources consumed by an algorithm form an important criteria for comparing algorithms. And what are the computer resources? The computer resources may be in terms of time consumed by an algorithm in sorting a particular sequence, the space requirement, and even the difficulty in writing the algorithm by a programmer encountered. So, taking these as three basic criteria for determining any better of any two algorithms, let us say what may be the further divisions. In the case of time, the time in the case of sorting algorithms may be further divided into two types of times, one required for comparing of keys and the other required for shifting of the values or assignments. So from this point of view, the various algorithms which we discussed may be given in the list, the table which is given over here. Please look at the table. We have the various algorithms. We are discussing their comparison only from the point of view of time consumed. I'll show that space requirement is almost same except in the case of divide and conquer algorithms, which we will discuss later on. So main resource which is consumed by the various algorithms for the purpose of comparison is time. And as I mentioned, time taken by an algorithm is of two types: comparison of keys and time consumed in assignments. The selection sort takes, if n is the number of elements in the list to be sorted, then the selection sort takes half n square roughly time in comparison, and 3 times the length of the list for assignments. Where insertion sort on the other hand takes 1 by 4 n square, that is, if n is the number of elements in the list to be sorted, then it takes 1 by 4 n square, that is almost half of the time taken by the selection algorithm in the matter of comparison of keys. That is, the number of keys which are to be compared is almost half in the insertion sort as compared in the selection sort. However, the number of assignments which are required to be made in insertion sort is the square of the length divided by 4. That is, the assignments to be made in insertion sort are much more as compared to selection sort. Shell sort cannot be analyzed in terms of number of comparisons and assignment because of its complexity. However, from empirically, that is through experiment on applying shell sort to a large number of sequences of numbers, unsorted numbers, it is found that n raised to the power 1.25 to 1.6 raised to the power n 1.25 for large number is the number of comparisons which are done, which is quite good comparatively as compared to n square. Next is heap sort. Heap sort takes 2n log n plus order of n in the worst case, which is not a very bad number as compared to n square. However, the number of assignments is also of the n log n. Quick sort takes 1.39 n log n number of comparisons of keys and 0.69 number of assignments. You can see quick sort makes very less number of assignments. Merge sort and quick sort, which I told, are two methods based on divide and conquer strategy. Both of these take much more space as compared to the rest of the extra space which is required. One space is required for storing the number of elements which are to be sorted. However, apart from that, apart from storing the elements to be sorted, merge sort and quick sort require extra space for storing the numbers. However, the number of comparisons is n log n to n log n minus something like this, and number of assignments is n log n. The merge sort is very good for linked list, but poor for contiguous list. It has been found through experimentation. The merge sort is very good for linked list, but very poor for contiguous list. And for linked list, comparison required are n log n to this one. Number of assignments in merge sort is equal to n log n. Quick sort takes about 39% more comparison than merge sort. It is experimentally found. So with this discussion of comparisons, we have come to a very important result which has been proved mathematically. And this result says, please look at the slide, any algorithm that sorts a list of n items by the use of key comparison must in its average case perform at least log n factorial number of comparisons, that is the number of comparisons on the average which are required to be minimum is n log n. That is, no algorithm which sorts a given unsorted list of length n on the average will make less than n log n comparisons. That is, if you n log n is the average minimum number of comparisons required for any algorithm. That is the significance of this law. Friends, so far we have discussed a number of algorithms and their relative time consumption, space consumption, etc. While finding out the comparative merits and demerits, we found a number of functions of the length are required to be computed. The number of comparisons for a list of length n may be some function 3n square plus 4n plus 6 etc., something like that, which is a function of n, the length of the list to be sorted. In order to make this comparison a bit simplified, some other mechanisms, that is asymptotic notations, are used in order to get a good idea but not the exact idea which algorithm is taking how much time for sorting a given list of n. For this purpose we require a few definitions. So this complexity of an algorithm is first of all measured in terms of the number of items in the list, which is called the size of a problem. In the case of list, it's very easy. If there are n elements in the list, then n is taken as the size of the problems. But in many other problems, the number of items may not be the measure of the size of the problem. For example, when you have to multiply two matrices of size n cross n, then we may take n square, the number of elements in one matrix, as the size of the problems. When you are taking into consideration a problem of polynomials, then the degree of the polynomial may be taken as the size of the problem. Size of the problem is a concept which cannot be defined apart from the problem under consideration. Only when a problem is there we can say this may be taken as the size of the problem, and then the next step is how to find out the complexity or the time consumed or space consumed in terms of the size of the problem. But as I mentioned and I repeat, that the size of the problem is a concept which cannot be defined for a particular problem in advance. Only when the problem is before us, we can assign a number, an integer, positive integer, in respect of the size of the problems. Then when we compute time, whether it is time for computing or the size of space requirement, it becomes a function of the size of the problem. Now, our main interest is not in that the function, how is the function, rather in the rate at which the function's values increases as the size of the problem increases. What is the reason behind that? Reason is, generally computers are used for solving problems which are very, very large sized. That is, we are interested in finding out the worth of two algorithms comparatively when the size increases. For smaller sizes, one algorithm may be better than the other. However, when n increases, that is, as the size increases, the other algorithms may become better. Then we will prefer the other algorithm. The reason is, for example, you have to find out the product of two matrices, and you have two algorithms, algorithm 1 and algorithm 2. Now, algorithm 1 is faster when we are considering the product of two matrices each of size 2, even of 3, even of 4. The first algorithm does very well. However, when the size becomes 100 or 1000, then the second algorithm is better. Then we will prefer the second algorithm. What is the reason? Because we don't use computers to find out the product of matrices which are of 2 cross 2 or 3 cross 3 size. We generally use computers to solve problems of matrix multiplication when the size of the matrices is maybe 100 by 100 or 1000 by 1000, etc. So if an algorithm which is good for larger sizes matrices will be the one which is preferred. Now, how it is expressed mathematically? Mathematically we say, as n goes towards infinity, the value of the complexities or time consumed by the two algorithm, whichever is faster, is not good. This notion can be formalized in the definition of asymptotic notation, but before that we take an example in order to clarify what is meant by which algorithm takes more time at a faster rate. Please look at the slide. For example, there are two algorithms in which for a problem size n. For example, we have to multiply two matrices, each matrix being n cross n. Now, one of the algorithms takes 1000 n square time. That is, if n is the size of a matrix, theoretically we assume that the first algorithm takes 1000 into n square number of steps, where the second algorithm takes 5 times of n4, that is, if the size of the problem or the size of the matrix is 2, then it will be taking 5 into 2 raised to the power 4. Now, in these cases, if our matrices are n is equal to 2 or n is equal to 3, you will see that the second algorithm, which is taking time f2n, will be taking much less time as compared to the algorithm whose time complexity is represented by f1. Because when we take n is equal to 2, the value of f1n will become 4000, where the value of f2n will become 2 raised to the power 4 is 16 into 5 is 80. That is, the number of steps which will be taken by the second algorithms will be 80, whereas in the case of first algorithm, number of steps which will be taken will be equal to 4000. This means we should prefer the second algorithms. But friends, it is a misconception. It is a misconception in the sense, as I mentioned, that we don't use a computer system for multiplying matrices of size 2 or 3 or 4. Rather, we use computer systems for multiplying matrices of very large sizes. But how we should know whether the time 1000 n square is less or more for large n's? For that, the notion of asymptotic comes, that is, you go on increasing the values of n towards infinity, and in the process when n is going towards infinity, whose value is getting more and more, faster and faster. The one whose value becomes larger and larger is not corresponding to a better algorithm. So what we do? We use the mathematics of limits. That is, in this particular case, we take limit f2n by f1n as n tends to infinity, and you can see 5 and 4 divided by 1000 n square is equal to n square, and n square becomes infinite as n becomes infinite. This means the ratio of f2n to f1n is going towards infinity as n. This means that the second algorithm will increase at a much faster rate as compared to the second algorithm. That is, the number of steps which will be taken by the second algorithm will be much more as n becomes larger as compared to the first algorithm. This means also in turn that we should prefer the first algorithms, which takes 1000 n square steps, whereas the second algorithm, which takes 5 and 4 steps, will be in the beginning for smaller sizes maybe taking lesser number of steps, but for larger sized problems it will be taking much more steps, and this is the basic idea behind asymptotic notations which we are going to introduce now. Friends, while finding time complexity or space complexity for a problem of size n, we are generally not interested in the exact function of n which will represent the time complexity or space complexity. Rather, we want to have a rough approximate. Why? Because exact computation may require much more time as compared to rough estimate, and through rough estimate most of the time we are able to compare two algorithms for their efficiency. And in order to have a rough estimate, there are 5 types of rough estimates which are used by computer scientists in order to to estimate the complexity of algorithms. And these are given in the table in the slide. Please look at the slide. The 5 asymptotic growth. I have already explained what is meant by asymptotic growth rate function. That is, a function's asymptotic growth means as n becomes larger and larger, what is its behavior in respect of growth in the values of the function is called asymptotic. Asymptotic means as n is approaching infinity. So there are 5 well-known asymptotic growth rate functions: big O, then big omega, then theta, and then little o and little omega. We'll discuss some of these in the process, but one at a time. We'll start our discussion with big omega. First we define it, then we illustrate it through a number of examples. So please let us have a look at what is meant by big omega. Big omega means if you have got big omega Gn, then in that case it actually represents all those functions for which there exists C and Gn. Order Gn, big omega Gn, big Ogn is the set of all those functions for which there exists a C, such that C of Gn is less than equal to Fn is less than equal to, or this complex equation or inequalities may be simplified by saying that a function Fn is such that the values of this function at n's as n become larger and larger become less by some constant multiple of Gn, then Fn is belonging to the class order Gn. That is, big Ogn represents all those functions whose values become less than the value of some constant multiple of Gn after some first few values are excluded. I'll explain these things through examples. Please look at the example. Let us consider this. We want to show that if fx is a function 2x cubed plus 3x square plus 1, we are to show that fx is equal to big O x cube. I explain the meaning of this. The meaning of this is that the function fx is equal to 2x cubed plus 3x square plus 1 is such that after some multiple of x cube is taken, then after leaving some of the earlier values of n, for all other n's, the constant multiple of x cube will have more value as compared to the value of 2x cube plus 3x square plus 1. That is the exact idea of big O notation. So friends, we explain this notion through the examples which are given on the slide. First of all, we should note fx we have taken as 2x cube plus 3x square plus 1. We want to show fx is equal to big O x cube. What does this mean? This means we should be able to find out a constant c which when multiplied with x cube, then the value multiple of x cube will have more value as compared to 2x cube plus 3x square plus 1. How it happens? Please look at the next slide. Now what is fx given? The fx is given as 2x cube plus 3x square plus 1. Now these x represent natural numbers, and for natural numbers we know that higher the power, more the value of the natural number. X represents a natural number, therefore its square will have more value than the number itself. The cube of a natural number will have much more value as compared to the number itself, and so on. So 2x cube plus 3x square plus 1. Now if we replace x square by x cube and 1 by x cube, then the right hand side, which is obtained by replacing x square by x cube and 1 by x cube will have more value. That is, 2x cube plus 3x square plus 1 is less than equal to 2x cube plus 3x cube plus 1x cube. That is, we have replaced all the powers which are less than x cube by x cube itself. X square has been replaced by x cube, 1 has been replaced by x cube, because the value of x square when x is a natural number is less than the value of x cube for x being natural number. And there, when we replace all the powers by x cube, we get fx is equal to 2x cube plus 3x square plus 1 is less than equal to 2x cube plus 3x cube plus 1x cube is equal to 6x cube. What does this mean? That fx is less than equal to 6x cube for all x. Thus we have found out a constant 6 by which if we multiply, then x cube becomes more than fx, therefore fx belongs to order of x cube. Friend, in this explanation we have taken into consideration two things. First of all, we are leaving a number of terms that is, we are not necessarily taking the early initial values of x, and secondly we are allowing multiple of 6. What is the significance of these two things? Why we are allowing a multiple 6 here and in general a multiple c? The reason is that while taking into consideration the computational time, the computer is not something fixed. Some computers may be very slow, the other computers may be very fast. So you cannot say that the is problem which is solved on a slow computer and on a fast computer is the same algorithm becomes better than this. No, the problem is something like this, that in order to compute the computational time in solving a particular problem, we don't take the actual time which is in microseconds and nanoseconds, rather we compute the number of steps. So this constant indicates the difference between the speeds of the various computers. That is a constant multiple. If one algorithm is time complexity when multiplied by a constant is less, then we can say it is better algorithm. So that is the idea behind the taking the constant. The other thing, when we are comparing two algorithms and their functions which represent their complexities are known to us, when we find out their values, the earlier values are neglected, as in the case of 1000 n square and 5 and 4 we saw that for n is equal to 3, 4, 5, 1000 n square will be taking much more number of steps as compared to 5 and 4. But still we will prefer the algorithm with 1000 n square, because for larger values of n, 1000 n square's value will become much less as compared to 5 and 4. So that is the reason for neglecting first k values. So friends, this is the basic idea of the two constants c and k in comparing two algorithms. Now next we show the fx square, which is 2x square plus 3x cube plus 2x cube plus 3x square plus 1 is of order x4. For that purpose, as we did earlier, here also we can replace each of the powers in fx 2x cube plus 3x square plus 1, each of the power x cube, x square and x raised to power 0 equal to 1 can be replaced by x4. We will be getting fx is equal to 2x cube plus 3x square plus 1 is less than equal to 2x4 plus 3x4 plus 1x4 is equal to 6x4. So again we are able to produce a constant 6, for which the value of fx is less than equal to 6 times of x4, therefore fx belongs to order x4. Next we think of another function, that x cube is of order fx. So in this particular case we have to produce a constant c, such that x cube is less than equal to c times of the fx, that is 2x cube plus 3x square plus 1. Now in this particular case we prove the result by contradiction. That is, this should not happen. So for that we assume that there are two constants. Whenever we have to prove a contradiction, we assume whatever is given is having the conditions which are satisfying ones. So in this particular case we want to show that fx x4 does not belong to order of fx, because for that we are required to show that there exists a constant c, so that x4 is less than equal to c into 2x cube plus 3x square plus 1 for all x greater than equal to k. So what is to be done in this particular case is we have to produce c and k which satisfy this condition. However, we will show that if we assume this is true, then we will not be able to find out some value of c or k, because what we'll do, if we assume that x4 is less than equal to c into 2x cube plus 3x square plus 1 for all x equal to k, what would happen? This means x4 is less than equal to c into 2x cube plus 3x cube, because x cube is replacing x square, that is by replacing x square by x cube we are getting a larger number, and because x4 is already less than equal to that number and that number is now being replaced by another larger number, therefore x4 should be less than this one. So now what we are doing, instead of 2x cube plus 3x square plus 1, we are replacing it by 2x cube plus 3x cube plus x cube, which will have larger values for each n. Therefore x4 must be less than equal to c into this, which is equal to 6cx cube. So if we assume our condition is true, then we will be getting x4 is less than equal to 6c x cube for all x greater than equal to k. Now cancelling out x cube from both sides, we get x is less than equal to 6c for all k greater than equal to k. But x is a variable which may assume any value of an integer howsoever large, whereas 6c is a constant. So how a number which is variable and is allowed to assume any value can be less than equal to a particular constant 6c? You can see if I replace x by 6c plus 4, then we will be getting 6c plus 4 is less than equal to 6c, which is wrong. That is, it is contradiction in the sense that we started with some assumption that it should happen like this, but that assumption led to a fact that 4 is less than equal to 0, which is not true. Therefore, there is something wrong with our assumption. That is, the assumption was x4 is of order 2x cube plus 3x square plus 1, which is not true. So, friends, next we show fx is not of order x square. Because again I have said that whenever we have to show that this function is not of this order, what we do, we prove it by contradiction. That is, we assume fx is equal to of order x square. And by this assumption we get something nonsense like 4 is less than 0. And because 4 is less than 0 is not true, therefore there is something wrong. And the wrong is with our assumption. And our assumption is fx is of order x square. With this assumption we are getting something wrong like 4 is less than 0. Therefore we should discard this assumption. That is, fx is equal to order of x square. The assumption is wrong. So let us start with showing, in order to show fx is not equal to order x square, we assume let fx is equal to order x square. What is fx? Fx is 2x cube plus 3x square plus 1, and we are assuming that is of order x square, and if it is to be of order x square, then there should exist a constant c and a constant k, such that 2x cube plus 3x square plus 1 is less than equal to cx square for all x greater than equal to k. This is by the assumption of the fact that fx is equal to order x square. What do? We divide throughout by x square, because the inequalities don't change if we divide by a number, and because x is a natural number and therefore x square is also a natural number, and natural numbers are, whenever we divide by a natural number both sides, the inequality is preserved. So on division by x square, what we will be getting, 2x plus 1 by x square is less than equal to c minus 3. And because 1 by x square is again something positive, therefore if we drop the inequality, should the number 2x plus 1 by x square becomes still lesser by dropping 1 by x square, so we will get 2x is less than equal to c minus 3. Now you friends see, x is a variable, c minus 3 is a constant. If I take the value of x is just as c, what will we be getting? 2c is less than equal to c minus 3. That is, c is less than minus 3, whereas c is a positive number. Again it is a contradiction. And this contradiction arises because of the fact that we have started with the assumption that fx is equal to order of x square. Therefore, through this contradiction we get fx is not equal to x square. Now we will find out the big O order of the sum of first n natural numbers. The first n natural numbers we know, 1 plus 2, 3 plus n, etc. Now Sn is equal to 1 plus 2 plus 3 up to n. Now each of the number 1, 2, 3 up to n is less than equal to n. So what we can do, we replace each of them by n. So we will be getting Sn is equal to 1 plus 2 plus 3 plus up to n is less than equal to n plus n plus n. These n's are there, therefore the right hand side becomes n square. So Sn is equal to 1 plus 2 plus 3 plus n is less than equal to n square. Therefore there exists 1 such that 1 into n square is greater than equal to Sn, and hence Sn is of order n. Friends, next asymptotic notation is big omega. This is used for best case comparison, that is, if omega function takes an amount of time, then no other algorithm, if an algorithm takes omega of fx time, then no algorithm can take less than fx time. In this particular case, the inequalities are changed. That is, if fx is of big omega gx order, then fx must be greater than equal to c of gx whenever x is greater than equal to k. Once again I repeat that big omega and big O notations. Big O notation is the worst case complexity measure, whereas the big omega is the best case measure of complexity, in the sense that if a particular algorithm takes omega fx time, this means no other algorithm having a particular function belonging to omega fx will be taking lesser time than this particular algorithm. So in this particular case, the inequality is reversed. That is the basic difference. The definition can be read from the slide. If gx is a polynomial of degree n, then omega gx includes all functions of degree greater than or equal to m and possibly other non-polynomial functions. Big omega describes a lower bound or used to bound the best case running time of an algorithm, whereas the omega x measures the worst case. Again we will find out, solve some of the problems in the case of big omega x. For a function fx is equal to 2x cube plus 3x plus 1 and hx is equal to 2x cube minus 3x plus 2, show that fx is big omega x cube. For this problem, fx is equal to big omega x cube. What we have to do? Please look at the next slide. In this particular case, we have to fx is greater than or equal to cx cube for all x greater than 1. Here the inequalities have been changed as compared to in the previous case, and we know fx is equal to 2x cube plus 3x plus 1. So replace fx by 2x cube plus 3x. We will be getting hx is equal to 2x cube minus 3x plus 2. Let c and k be greater than 0 such that 2x cube minus 3x square plus 2 is greater than cx cube, and ultimately on simplification we get the value of c is 1 and k is equal to 3, satisfies the last equality, and hence the proof. We take the third part, where we have to show 2x cube minus 3x square plus 2 is equal to omega x square. What does this mean? We have to show that 2x cube minus 3x square plus 2, there exists a constant c, so that 2x cube minus 3x square plus 2 is greater than or equal to cx square for some x greater than or equal to k. Now again it can be seen that lesser the value of c, better the chances of the above equality becoming true. So to begin with, let us take c is equal to 1. If we take c is equal to 1, then what will we getting? We will be getting 2x cube minus 4x square plus 2 is greater than or equal to 0 by replacing c by 1. And for x greater than or equal to 2, the above inequality holds. Therefore we have found out the values of k being equal to 1 and c being equal to 2, so that this equality also holds. Similarly, we can take the next case. Let the equality x cube is equal to omega 2x cube minus 3x square plus 2 be true. In this particular case, we will show that it is not like that. So what we will be doing, x cube is greater than or equal to c into this, and in this case c is equal to half and k is equal to 1. Again the inequality is satisfied, and hence the x cube is of big omega 2x cube minus 3x plus 2. So friends, these are two functions which we have already discussed, big omega and big O notation. There is a third notation which is called theta notation. As we already discussed, that big O provides a lower bound on the complexity of an algorithm, and big omega provides an upper bound. However, in some of the cases we want complexity function which gives the equality. So in this particular case the theta notation is used for the definition of this. Let fx and gx be two functions, each from a set of natural numbers or positive real numbers to positive real. Then fx is said to be theta gx, pronounced as big theta of gx, if there exist positive constants C1 and C2 and K such that C2 of Gx is less than equal to Fx is less than equal to C1 Gx for all x greater than K. What is worth noting is that the function Fx, which is of order theta of Gx, then the value of x must lie between some multiples of the values of gx at corresponding point. If it is to be of theta notation, it must be bound on the lower side as well as on the upper side by some multiples, constant multiples of the values of the corresponding values of fx. In this particular case it can be shown for any two functions fx and gx, if fx is equal to theta gx, if and only if fx is of big O gx and fx is small big of omega gx. The theorem is beyond the scope. However, we can relate the three functions big O, big omega and theta through this theorem, which says for any function fx and gx, if fx is equal to theta gx, if and only if fx is of big O gx and fx is big omega x. For the following function, show that again we will be showing some of the equalities. Fx, if fx is equal to 2x cube plus 3x square plus 1, then fx is big omega x cube. Fx is not equal to big omega x square, fx is not equal to big omega x cube. So first of all we establish the first equality, fx is equal to big theta x cube. For this please consider, for c is equal to 1 and c2 is equal to 1 and k is equal to 1, we get c2x cube is less than equal to fx is less than equal to c1x cube. Please look at these again. We have to show that 2x cube plus 3x square plus 1 is such a function that it is less than equal to some constant multiple of x cube and it is more than equal to some constant multiple of x cube. And you can see, because 2x cube plus 3x square plus 1, if each of the power of x is replaced by x cube, then it will be less than equal to 6x cube. So if we take c2 is equal to 6, on the other hand, if each of the powers 2x cube plus 3x square plus 1 is replaced by 1, we will be getting 2 plus 3 plus 1 is less than equal to x cube. So friends, we have shown there exists c1 and c2 which satisfies the condition of theta. So with this I hope that you may be able to understand how to sort given sequences and how their complexities are computed approximately using asymptotic notations. Thank you.